from the yesterday's contest, and maybe we'll have time to also talk about some of the tasks from the previous contest. We didn't have time.
Teacher.
To talk yet.
Professor?
Yeah.
May you use the
microphone? Okay, sorry.
Turn it on.
Okay. Now it's better? Okay. So from the yesterday's contest, we have some easy tasks to skip, like DNA and planets. There were no surprises there. The task coins was also not very difficult, but we have some nice technique in it, which you can use in different problems. So we will talk a little bit about it. Okay, so coins. So in this task we have a sequence of throws of coins, and in every throw we can have head or tail. And we also have number k. Let's say k is equal to 3, and we want to find the longest fragment of this sequence, in which we have exactly k times more heads than tails. So, for instance, this is the whole array here is the correct fragment, because here we have 6 heads and only 2 tails. So we have exactly k times more heads than tails. So we can just apply one trick here. We can just replace every head with 1 and replace every tail with minus k. So we just put here plus 1 and here we put minus k. And then we can just make the prefix sums of this in this sequence. So here it will be 1, 2. Okay, so minus k is equal to 3 in our example. So here we have minus 1, 0, 1, 3, minus 1, 0. So it's easy to see that in order the fragment is good if it has the sum of the numbers in this fragment is equal to 0. So in our case, if we have this, we can just think about only these numbers, and now our task is to find the longest fragment which sum is equal to 0. So if we have like another set of numbers, plus 1, minus 3, plus 1. So what is the property of the fragment so the fragment is okay. So as we said before, this fragment should have sum equal to 0. But we can also compute the prefix sums for all the numbers. So this way it will be 1, 2, 3, 4, 1, and again 2. And how do we phrase this property in terms of this sequence? So if this fragment has sum 0, so the prefix sum of the last element should be equal to the prefix sum of the element before the first element. So if the range from A to J is okay, only when the prefix sums of I minus 1 is equal to prefix sum of J. So we can just calculate all the prefix sums, and we will be storing in a map all the occurrences of all the possible sums. And if we find the second occurrence of the same sum, then we can just say, okay, so this is the correct fragment. So the code is really short. So we can first we can say that the where the prefix of, well, if you have no numbers, then the sum is equal to 0. So we can say that for the sum equal to 0, the first place it occurs is just before all the numbers. So the first place is 0. And okay, and now we go from 1 up to n. So the length of our array is n. And we just first, we can just store the prefixes in the, we don't need this array actually, so we'll just store the prefixes in one variable. So then we just add this now, add additional number, and then we can find if in the map, if map contains the sum. So actually, if the map contains the sum, so we know that the fragment which ends in element I and which begins in element which is stored in the map is the correct fragment. So we can just say that, okay, so in this case, fragment from map of sum I is okay. And we can just see what is the size of this fragment and update the answer. And if we don't find the sum, we just update the map. So in the second case, we just say that map of sum is equal to I. So actually the first place we see the sum equal to sum is in the ith element. So the time complexity of this task of this solution is n log n. Okay. Okay. So as the second task, we will talk about the clients. So we have some clients, and these clients must be served by a clerk, and we have for every client we know how much time it takes the clerk to serve this client. So actually for the ith client we have two values, AI and yi. And the time to serve this client, if this client is, the starting time of this client, if it is t, then the time required to serve this client is equal to AI times t plus AI. So this time of serving depends on how long does this client have to wait before it was served. So if he waits longer, then probably his time will get bigger. So in this task, we want to find the order of serving the clients, in which all of the clients will finish as soon, well, in the minimal time. So we are interested in the minimal time of serving all the clients. So this task is similar to the task the hero, because also in this task we have to find some kind of best ordering. So usually in this task can be solved using some kind of greedy solution, and in order to prove that the greedy solution works, we did the one thing. We fixed some ordering, and then we changed the order of two adjacent elements in this order, and we try to figure out how this change affects the outcome. So let's do this also here. So let's assume that we have two guys which are in the order. So first we serve the guy this one, and then we serve this one. Maybe I will just use the. I and J are very similar. Let's use the K. So we have two guys. So before this guy, possibly we'll have some other guys which will be serving, and the serving of these guys finishes in time t0. Then we will serve this guy, and then we will serve this guy, and then possibly some other guys. So let's see what is the time to serve all of these guys and these two. So first of all, we need time t0. Then we need time to serve this guy. So we need time a1 times t0 because he's starting with 0 plus bi. Then we need to figure out how much time does it take to serve this guy, and this is ak times. So in which time he started? Well, he starts it in this time. So it takes t0 plus ai t0 plus bi plus bk. Okay. So this is the time we finish these guys. Okay, so now let's swap them, and let's see what happens if we serve them in the other order. So now we serve the kite guy, and now after that the I. Okay, so the reasoning is similar. We just have to rewrite it, replacing all the i's with k's and vice versa. Okay, so we have these two numbers. And we would like to compare these numbers to see which is better. So in order, if you want to compare them, then we can just erase all the same terms from them. So for instance, you can just remove t0. So let's write this. Okay, so let's rewrite this. So for instance, we have t0 plus I1. Also we have t0 here and here. And then we also have bi and bk. And what we are missing? We're also missing ak times bi. And let's do the same thing here. So we have t0, again it's 1 plus ak plus ai here plus ai times ak. And we also have bk and bi, and finally we have ai times bk. Okay, so these sums look very similar. Actually, the thing in the parentheses here is exactly the same, and then these terms with bk are also exactly the same. So we can just, if we want to compare these numbers, we can just remove it. So in order to compare them, we only how to compare these numbers. So if we want to check whether this ordering is better, we have to check whether this number is smaller than this one. So it is equivalent to check this inequality. So if we divide both sides by AI and AK, we get BI times A1 is smaller than BK and AK. So actually, this time is smaller if the ratio BI AI is smaller than this ratio for this guy. And we also have to see how this affects the other guys. Okay, so these guys are not affected by changing the order, but by how changing the order affects these guys. So actually, if all of these guys start in a smaller time, then it's okay for them. Okay, so it's always good for us, like, to, without changing their order, if we start them in some smaller time, we will have at least the same, at least as good solution as we had before. So we can just exchange them. If we exchange these guys and we get the smaller time, it's okay for us. So actually, we can sort all of these guys using this ratio. So we can start with guys with the smallest ratio, and it will be good for us. So actually, we can just write the comparator. So for the STL sort. So let's say we have we want to compare two numbers, or two indices, whether it's better to put I in the front or J in the front. So we can just say, okay, which one is better? Well, just return BI divided by AI. So let's just say that this ratio is. But this is not cool enough due to the precision. We have do here the division. So actually, it's better to write this in this way. So instead of comparing the ratio, this is the equivalent. So we can do multiplication without using the precision. So so we can just write this AK times BI minus AYBK. So this must be smaller than 0. But here we have, in this question, we are supposed to, if we have more than one answer, we have to return the answer which is smallest lexicographically. And actually we have some, if these two ratios are the same, so it does not matter in which order these guys will be served in order to get the minimal time. So we may serve them in any order, but we would like to then serve them in this order that the guy who has the lowest number comes first. So actually we can first calculate this value, and then if this value is not 0, then we say true if this value is smaller than 0. And else this value is 0, so these guys can be served in both ways. So we say that we will sort first this guy who has the lower number. Okay, and many teams got the solution, because actually this problem is not very new. It's quite known. So many teams got the solution and they got wrong answer from the judge. Because here we have a little twist. So let's see at this part. So we divided both sides by AKI and AI. So we actually made an assumption here. We assume that AIs are greater than 0. And in the task statement, it says that both of these numbers can be equal to 0. So we'll have to be careful here. So actually this solution works if both of these numbers are positive, then you will get accepted. But if some of these numbers can be 0, then we will have to be extra careful. So let's consider, so actually we can consider four cases. If both of these numbers are positive, or if some of these numbers can get negative. So if BI is 0 and AI is positive, then here we got all of these numbers will be 0. So these guys will be served as the first guys. And actually it's okay, because they will B0 is equal to 0, so they will not generate additional time. So all of these guys can be served like in no time. The second case is if B is greater than 0, but A is equal to 0. Then we can say that here we have like infinity in this fraction. So all of these guys can be served like at the end of the cube. And actually it's again good, because for these guys, because A is equal to 0, for these guys it does not matter when they are served. They always have take the same amount of time to be served, no matter when we start with them. So we can also put them as the last guys. So if we have these cases, so actually our code will still work. Yes, because here these things will work. The real problem is with guys for which both numbers are equal to 0. Then we have not even like interpretation for this fraction 0 divided by 0. So what about these guys? So actually these guys can be put anywhere in the cube. So first of all, they can like if we put them anywhere, they will not affect any other clients, because the time of serving them is 0 and they don't generate any additional time. So actually we can put them anywhere. In fact, our comparator here will not work with them, because if you use STL sort, the comparator you provide must satisfy some axioms. So actually this comparator, for instance, if you compare numbers I and j, and you have this comparator, so for instance, comparison of I and I must be false. If comparison of I and j is true, then if we change them, it must be false, and also this must be transitive. So if we compare A with J and J with K, then also comparison with A and K must be true. So in other words, this comparison you have here, it must behave like the less than. So it has to behave like this operation. And actually, if your comparator violates some of these axioms, then your code is well, there's no guarantee that your code will work. It can even crash, get you the runtime error. If your comparison, because STL sort actually assumes that all of these are true. So let's see what will happen here. So let's say that we have like guys on positions 1 to 3, and this guy has values 0 and 0. So actually, if here we put 0 and 0, so this will be always equal to 0. If we compare anything with this guy, this v will be 0, so we will compare it with using this inequality. So actually, we will have that 1 is guy 1 is smaller than 2, and 2 is smaller than 3. Yep. And no matter what is the relationship between 1 and 3? So actually, if this guy has no zeros, the relationship between them is based on these numbers. So if this guy is like let's say 1 and 2, and this guy is 2 and 1. So actually, if we want to compare 1 and 3, so 1 will get the fraction of 2, and 3 will get the fraction of 1/2. So actually, this fraction is greater, so 1 would be greater than 3. So we have no transitivity here. So if we just put also the zeros here, probably we will get, our program will crash. So what can we do? So actually we will maintain two lists. The one list which will consist of all of the guys which are not 0, 0, and we will just sort them using this function. And the second list which will consist of all of the guys who are 0, 0. And we have two lists, and we have to then we have to merge them based on the numbers of the clients. Because we can put 0, 0s everywhere, anywhere, and we want to find the solution which is lexicographical smallest. So we will put them. Well, we will merge them. We'll merge the lists using this comparison, and then our program will work. And of course, because like most of the time we will spend doing sorting, then the solution takes n log n. Okay, that's it. Okay, so one more thing here. So as I said, some of you knew this problem before. So after you coded this solution, you could be quite tempted to think that the judge has some error in the tests, because like you know that this solution should work. But usually on the contest, you shouldn't go with this. Like, you should then try to once again read the problem statement carefully to see if there are some corner cases you possibly could miss. Because yeah, the judges usually have much more time than you to prepare the solution, and usually they're correct. So I would say that in this case, like, try to reread the test statement once more in order to see if you're getting everything correct. Okay, so now we will go to some 3 problems. We had 2 of them on the yesterday's contest: prison escape and trip. So we will do them. We'll do them now. Okay, so in the prison escape we have a tree and some nodes. And some nodes of this tree are special. So the story was that this tree represents a prison, and so in some nodes are cells with prisoners, and these cells get open, and the prisoners are about to escape the prison. So we want to put guards in some of the blue vertices. I mean, red vertices will represent cells with prisons, and we want to put some guards in blue vertices in order to block any route of escape. So we say that prisoners from this node can escape the prison if there is some path from this node to the leaf of the tree, and on this path there are no guards. So actually here we can put the guards in all of the leaves of the tree, and then we will block all of the routes of escape. And we want to calculate how many guards we need in order to prevent the minimum number of guards. So, as I said, if there are no prisoners in the leaves of the tree, because if there is some prisoner in the leaf, then we cannot stop him from escape. So in this case, there is no solution. I mean, every number of guards will not be sufficient. So let's assume that all the leaves are free, meaning all the leaves are blue. So in this case, we can just select all the leaves. But as you can see from this picture, it won't give us the minimal answer, because here we have 3 leaves, and it is sufficient to take only. It's sufficient to select these 2 nodes in order to block these guys. So the second idea would be, okay, so let's block all the neighboring nodes from the red nodes. And then again, it's not good idea, because let's say we have this kind of example. Okay, so here we have two red nodes, and if we are about to block every neighboring cell, then we will block. We obviously have to block these guys. So in this case, we will block this guy and this guy. So we would use four guards, but actually we can do with 3. So actually, in this case, it's better to put the guards in the leaves. So if we put the guards in the leaves, then we'll have the optimal answer. But it's not like we can take the minimum of these 2 solutions, because we can make this prison even more big, and then we will have to either take this guy or this guy. So these are not. So in order to get the optimal solution, we don't use leaves or cells or neighbor. So other approach will be, okay, so let's say we have some. So first of all, let's put some cards in the leaves, and then if we can, and then let's just, and then if we can, like, if you can take this guard and move him downstairs, and this move will not block anything. So then we will just start. We'll just start erasing leaves. If we can erase leaf and have still possibility of placing the guards, then let's do it. So actually, if I have a leaf, and this leaf is connected to a blue node, then I can just remove this leaf. Because I don't have to put the guard in this leaf. If I put this guard in this blue node which was connected with the leaf, then still I removed any route of escape. So let's just do this thing. So in our case here, it will be as follows. So I have a leaf and he's connected with a blue node, so I'll just erase it. And say, okay, so I think I have to like put the guard here. So again, here I have a leaf, so I can erase it and say, okay, I need a guard here. And then this leaf is also connected with the blue node, so I can just erase it and say, okay, so I will put guard here. And then in this case, I will get the correct solution. But that will not give us an optimal one. So let's consider another case. Okay, so here I have to take this one, I have to take this one, and again I start from the leaves, and I said, okay, I will take these leaves, and again every this leaf is connected with the blue vertex, so I can just erase them and say, okay, so I have to take these guys instead. And as you can see, now we need 5 guards to do the job. Well, we selected 5 guards, but we only need 4 of them because we don't need this guy. So what can we do? So actually, we can be still another clever approach. Okay, so we did some. So what is the problem with this guy? The problem with this guy that he is not even reachable from the red vertex. Yes, if we go from the red vertex and go anywhere, and if we stop with the guard because the guard is blocking the way, then we can like see which guards are essential in this solution. So these guards are essential because they are reachable from this node, but this guard is not essential. It's not reachable. So we can just discard them. So we can just another solution. Okay, we found some guards, and then let's see which are reachable, and let's remove all of them. These ones which are not reachable, and let's see if maybe this is the correct solution. And again, it's not correct. So again, we can make another even more bigger prism.
Yo le expliqué a Martín
Sí, me dijo. Pero es parecido a veces.
pero habría que haberlo pensado más en papel, no parchearlo tanto.
Okay, so let's see what we have here. So again, this guy. So if we have leaves which are connected with the red vertices, we have to put guards in these leaves. Okay, so let's again. Our algorithm started from the leaves, so we have 4 of them. Then we started, if the leaf is connected to a blue vertex, we remove the leaf. Okay. And then we see which guys are reachable and which are not. So actually, in this case, all of them are reachable. Yes, because these 2 are reachable from these vertices, and these 2 are reachable from this one. So here apart from these 3 guys, we need another 4. But actually, it's easy to see that here we need only 3 because if we remove these two and put the guard here, we will have the better solution. Okay, so this task was really tricky because we have here like several levels of the greedy solution, and it's not very easy to create these counterexamples for them. Okay, so I prepared them beforehand when I was preparing this task, but during the preparation I also was tempted to go with some of the solutions, and yeah, so it wasn't very easy to convince that to find those counterexamples. So let's forget about greedy. Let's do dynamic programming. It always works. Okay. So first of all, let's observe that we can do each component in the graph. We can do separately. So which is a component in the graph? So if we select some blue node, and then we select all of the nodes which are not blocked by the red nodes. Yes. So for instance, in this graph, we have 3 components. We have this one, and this one. So a component is some blue nodes, and in the leaves of the components we can have either leaves or some red nodes. So we will root this component in some node. Let's say that the root is not a leaf. So the root will not be either the leaf or the red node. The components which doesn't have blue vertices which are not the leaves are small and can be done separately. So let's say we have a tree, and so our tree looks like that. But we have some nodes. Possibly some nodes are red, and if they're red, they're in the leaves. Okay, so we will be doing dynamic programming from bottom to top, and we will be just removing the vertices and possibly possibly placing some guards. So we have different possibilities here. So for instance, if we have this node in which all of the children of this node are blue, well, all of the children are leaves, then we can just remove these leaves. So if we have this situation, and here we have a blue node, so we can just say, actually it will be, okay. So we can just say that, okay, we can remove all of them and leave it as the one vertex. Because if we want to put guard in one of them, then it's better for us to just remove them and put the guard here. Okay, so we have another case. If all of the children of the vertex are red, so if all the children contains the prisoners, then we have to block all of these nodes, and we don't have any other path in this subtree to put the guard. So we can just say, okay, so let's remove all of these nodes, and let's color this node red. because it's the same like blocking this all of these guys. It's the same like blocking this guy. Apart from the thing that we can put a guard here, but okay, this won't be a big problem. Okay, we will come back to this. And now we have another case when some of the nodes are blue and some of the nodes are red. Okay, so then we have to block these guys, and actually we have to block them soon, because these nodes mean that there is some path to the leaf. So if we don't block this guy, then all of these guys can like escape here. So we say, okay, let's remove all of these guys, and let's put here like a special vertex. So let's call it a vertex plus. So first of all, we will have to put a guard here. So we will put a special vertex here, and we will say, okay, we have to add 1 to the answer. Add 1 to the number of guards. Okay, so once again, now we have a additional special vertex, and this vertex means, okay, we have some in the subtree. Probably have some guards. We will have some red nodes and we have some leaves, but we are guarding this tree already. So we put a guard there. So actually we can safely put this node also here. So if we have some additional nodes which are plus here, or here, or even here, they are of no importance, because all of the prisoners are guarded here. And also we will have another case in which we will have only nodes with guarded prisoners. So then we'll just merge them into this kind of vertex. Okay, and actually that's it. If we merge all of them and we will result with the one vertex, then this is the answer. So actually we also have to be a little bit careful in the root. So for instance, from this perspective, if we put all of the red guys in one place, no. So actually it won't be a problem here. Yes. Because these guys will not have any place to escape. So we actually didn't block them, but as long as we not have this thing, I mean this example that we have some leaf, so these guys will not escape anywhere. So this case is also correctly covered. So how can we do implement this? So we will just for each vertex we will just say in what state this vertex is. So we have 3 possibilities. So like we can make this array of. So for each vertex we will say either 0, 1, or 2, depends on which kind of the vertex it is. Actually, we don't have to store this array. We can just do a recursive thing. So if we do not have red vertices, then our resulting vertex is okay. Let's start with this one. So if all of these vertices are, let's say this one is 0, this one is 1, this one is 2. If all of these vertices are 2, then our root is also 2. If we do not have red vertices, then the root is 0. If we do not have blue vertices, then the root is 1. And if we have some blue and some red, then the root is 2, and we have to update the answer. And this runs in time complexity of O, like pretty much every simple diagram programming language. And we will have to do this for each component separately. Okay, so that's it.
No tiene que ver el caso de que un rojo en el medio. Cuando tiene un rojo en la punta, en el medio.
Por cómo genera componentes. Ya, todo el rojo está en raíz, en las hojas.
Sí, pero poder tener qué parte que va a tener rojo, hoja.
Okay, so let's stay with the second task with trees, trip.
Ah,
Pero en ese caso lo tienen que ver ahí.
So in this task we have a tree. And we want to select some connected fragment of this tree. So let's suppose we can select this. We want this fragment to be as big as possible, but not bigger than k nodes. So we also have number k. Okay. So we want this fragment to be as big as possible, but not bigger than k nodes. And also, every node has some value attached to it, and we want the nodes in this selected fragment to have values of at least as big as values in all of the other nodes. So if we have some value v here, and in some node which is not taken we have value w, then v must be greater than or equal to w. So like we want to take only the best nodes. So one of the problems in this task, which was clearly mentioned in the task statement, was that these nodes can have the same values. I mean, the values are not unique. But let's first try to solve the task, which is somewhat easier. And in this easier version, all of the values will be unique. Okay, so if we want to find the... So then in this version, v must be strictly greater than w. So actually what we can do, we can first sort all of the vertices by their weights and add vertices one by one, starting with those which have bigger weights. So then we'll have some tree. So let's say that. So let's put also some values here. Okay. So we are starting. So we are adding the vertices starting from these which have the greatest value. So we will have add 7. And actually, this is the correct one possible fragment, because this is connected. So we just update the answer that the answer is at least 1. Then we add 6, and still this is connected. so the possible answer can be 2. But then we add 5, and then we lost connection here. So this will not be a possible answer. But after we put 4 here, and after we put 3 here, we regain connectivity. So 5 will also be possible answer. So if k is equal to, let's say, 6, then actually this will be the best answer. 5 will be the best answer, because if we want to add the 6th vertex, then we will have to add this one, and then we will not have connectivity here. We will still need this one and this one, and the whole tree has bigger number than 6. So yeah, so this one is actually the correct answer here. So we have to do 2 things. First, we have to sort all of these vertices, and then we have to add them one by one and maintain connectivity. So we have to maintain disjoint sets, because during this algorithm, like we add here 2, and then we add 1, so we have 3 disjoint sets. So we can maintain them using the known structure for disjoint sets, using find and union. And every time we add another vertex, so let's say we add here 0, we will try to see for every neighbor of this node, can we add this node to another component we selected. So we also maintain the number of different components we have, and when we add a vertex, we add 1 to the number of components. When we try to see if the neighbor of this vertex is in different component, then we just merge 2 components and we decrease the number of components, and we only update the answer if the number of components in our tree is equal to 1. Okay, and this can be done in nlog_n. Okay, but this is the easy case, when weights are unique. Because if weights are unique, we actually know the precise order in which we have to add vertices. So let's say that weights are not unique. So what to do now? So like in the task with ascending paths, then we also had the problem with edges which have not unique values, and then in this task we added them in groups. So we added all all edges with the same value at the same time. So let's do the same thing here. So let's add all of the vertices with the same value at the same time. So let's say that we have some tree. And we already selected some of the nodes with the greatest value. So that gives us, let's say, two different components. And now we have to add a group of nodes with the same value. So let's say that these nodes are here. Okay, so let's say that these nodes are here. So actually, if we have this, so we have here the path from one component to the other, and if on this path some vertices are missing, so then we can just add all of these blue vertices, because adding them will not regain as connectivity. So the answer will be not. So we will not be updating answer in this for these nodes. So let's assume that the more hard part, when actually adding these guys will regain us connectivity here. So we can partition those nodes into different categories. There are some nodes which we will have to add, because now the thing is we can add them in any order we like, because some of them can be in a selected set, and so some of them don't have to be. So we would have to know the precise order in which we have to add them. So some of the guys like this here, they must be added, because thanks to them we will regain connectivity. Some of them, like this one, we don't want to add, because if we add this guy, then we will break connectivity. And there are some other guys which we can add, but we don't have to. So these are these guys. If we add them one by one, then we'll retain connectivity. And also these guys. So from these guys, we can add them one by one. So we can add any amount of these guys. So this is our yes, this is no, and these two are maybe. And what we like to calculate is to calculate the sizes of these sets, because so let's say the size of the red ones is count. So if after adding yes nodes we will have connectivity, then we can update the answer by count plus. So if this count plus yes is less or equal to k, then we can update the answer. And then we update the answer by value. So answer will be maximum of answer and minimum from k, because we can add as much as k, and count plus all of the vertices which we have to take, and some of the maybe vertices. So we would like to take as much as maybe vertices as possible, but no more than k. So actually, if this is true and we get connectivity, then we can update this answer. So the question is how do we find the sizes of the sets? So we can make a DFS starting from each vertex for each big blue vertex, and then making this DFS, we will find the. First of all, we can find the sizes of these components. So we can find the size of this component, and also we can find in how many places this component connects to other components. So here we will find 3 components. Actually, these guys will be in one big component, and this component does not touch the red component. So actually, the guys in this component we don't want to take them. So these are no guys. These guys are connected in only one place with the red component. So these are maybe guys. And then this component connects in 2 places with the red guys. So actually, this is the component which will make the connection possible. Some vertices in this component are yes vertices, and some are the maybe vertices. But we don't know still which one are which. So actually, after the first DFS, we can find the total number of these vertices, and we know that this component joins at least 2 other red components, and then we can also remember in which vertex, one of the vertices which connects red components. And then starting from this vertex, we can do another DFS, which will find all the paths to the other red components. So actually, this DFS will find this path, because this path is for other red components, and every vertices which are on the paths which connects two components, they are nested vertices. And all of the different vertices are maybe vertices. So that's it. And after updating the answer, we go to another step. So we go to the vertices which have strictly smaller weight. So before we go to another step, we just add all of these vertices to the graph. So this distinction was only needed in order to update this answer. But afterwards, we still have to add all of them to the graph. Okay, and so so the time complexity of this solution is also the same, because we have to first of all sort the weights of the vertices. All right, so this was kind of tricky. Actually, the implementation of this algorithm is not very straightforward, and also like seeing all this kind of possibilities is not very obvious. Maybe these guys from this component, these maybe guys which are in this big component are the most not obvious ones. But here we had like a common approach to the problem, because we started with the problem which is somewhat easier, and we devised the algorithm for the somewhat easier version, and then we tried to generalize this algorithm for the harder version. And usually we will do this kind of stuff. But actually, for this problem, there is a simpler solution. And in terms both of terms like explaining it and in terms of programming. So let's. So in this solution, we took the nodes in the order of the weights. So we pretty much know the order in which we would like to take the vertices, and then we had to see every time whether we still are connected or not. So we maintained the order of the vertices, but perhaps we lost the connectivity. So we can do the other way around. We can maintain the connectivity, and then so we will try to add nodes in this order in which we still have the connected component, but then we will face the problem in which precise order we will have to add them. So yeah, but let's do this. So the first thing also in this algorithm is to see what are the nodes, which node is the first one to take. So if we see all of these nodes with the highest weights in the graph, so let's say that we have some graph, and these guys are the nodes with the highest values. So then we know we have to start from some of the vertices, and in order to get the in order to be connected, we first have to select one of the connected components. So let's select one of these which have the most vertices in it. So we will start from this connected component, and let's assume that we have already some vertices which we talked to. So we have this connected component, and then we want to add another vertex which is, so here we have some vertices which we took, and now we want to add one of these guys. Yes, because we want to maintain the connectivity. So the thing is, which one should we add? And we can do greedy here. So we can. So if there are some vertices, which some of these vertices can have bigger values than any other. So let's say we have two vertices. This one has value 6 and this one has value 5. So which one is better to take? Well, of course it's better to take 6, because if we would if there is a solution in which we take 5, then in this solution, because 5 is greater than 6, then in this solution we will have to take 6. So in this case, it's better to take 6. So if the 6 has the greatest value from all of these vertices, has the unique greatest value, then it's easy to say, okay, take a 6. But what if we have two vertices with the same value? Then it's not. Then we can't take any of them. We need to see what's happening in the subtrees of these vertices. So what can happen? So for instance, this guy can have like vertices of small value, and this one, let's say that this one has some vertex of the bigger one. So this one has 7. So if we want to take any of those 6 vertices into our solution, then we will have to first take the 7, because the 7 has the greater value. So actually there can be a solution in which we take 7 and all of these vertices up from this path up to 6, but we do not take, actually this one also will take 2, so this is not a good example, but if we have here like 6, then we can take all of this and do not take this one. So actually in this case we have to first take this 6, but only because in the subtree of this 6 we have the element of greater value. So actually we can, this is the only information we need here. So from each subtree we will also compute what is the element of the greatest value in the subtree. So in this subtree the element of the greatest value is 6, it's in the root, and in this subtree the element of the greatest value is 7. So we will be breaking ties using these red values. So if we have two 6s, then we will add this 6 which has in the subtree has the element of greatest size. And actually that's it. So if we take the elements in this order, and then afterwards we also have to, we maintain connectivity, but we also have to check whether the vertices we already selected are the vertices which are greater than vertices not selected. So perhaps if we have this, so if we select this 6, so then it's a subset of some correct solution, but it's not still a correct solution, because here we have the element 7 which is not selected. But we can just make an array in which we store the number of each values, how many values of each kind we take, and what is the minimal value. And if we see that the minimal value is, let's say, 6, and we still didn't get the vertex of value 7, then this subset is not correct yet. So we will have to add more elements to it. And actually, we can do also the other way around. So we can compare our vertices based on the red numbers and take the vertex which has the bigger red number and then break ties using the blue numbers. So it's also correct. It's so we have like two really more or less equivalent to greedy solutions. And in order to calculate those values for all the trees, we can do simple dynamic programming. So actually this solution is even faster because we do not need to sort the weights of the vertices. We only have to find the maximum the component with the maximum vertices, and this can be done in linear time. So this solution takes linear time. Okay, that's it. Okay, so these problems were not so easy, and let's make some interruption here, and let's talk about one of the easy problems from the first day. So there was this problem called film editor, and the surprising thing was that this problem didn't get much attention from you, but it was not very hard. So we will not discuss the whole solution, but just to give you some ideas. So in this problem we got a string which was contained with letters D and S. And this string represented film roll. And in the film we have some scenes, and some scenes can be dynamic or static. So every dynamic scene is represented by letter D, and a static scene is represented by letter S. And we would like to edit this film because we very like dynamic scenes, and we think that the longer dynamic scene is, the film is more interesting. So we would like to have the longest possible dynamic scene. But we don't want to mess with the chronology of the film much. So we are allowed only to make K cuts. So we can do K cuts in order to make the longest dynamic scene as long as possible. So for instance, in this case, if K is equal to 0, then the longest dynamic scene is this one. It has only 2 scenes. If we can do one cut, then we can cut here, and we can just move this part. We can just take this part and move it here. So we will have the scene, because we can just glue the resulted pieces in which order we like. So then we will have the scene which has size 3. And if we can do 2 cuts, then we can make a scene of size 4, because we can start with this, then put this one and this one. So we can make it this way, so we can get a scene of size 4. So what do we have here? So actually from this example we see that we are interested in 3 different kinds of scenes. Well, not scenes, but pieces, fragments which we got. So if the resulting scene, which is the longest possible, so let's say that if the optimal solution is like this. So, and if the optimal solution consists of several pieces, then we have 3 kinds of pieces. First, we have like the prefix piece, which can contain some static scenes but must end with some dynamic scenes. Then we have some number of infix pieces, which contains only dynamic scenes, and possibly we have some suffix piece, which must start from some dynamic scene but can also have some static and dynamic scenes later. So we can do dynamic programming here. We will be just collecting the fragments we would like to cut. So if we have our string, we can be interested in some prefix of the string, and we can say, okay, what is the best solution if we just take the prefix of this, so the prefix of length I, and if we use some number of cuts here. So what is the best solution if we do some cut here and do probably some other cuts here. So the prefix of length I and using J cuts. What is the best solution we can find? And also, so we do some cutting here. We rearrange some of these values, and what is the best we can get? And also, we must remember whether we used the prefix or whether we use the suffix fragment. Because, well, these fragments, we can rearrange them in every way we like, but we can only use one prefix fragment and we can only use one suffix fragment. So we can also store in our state 2 flags. One flag which says, oh, did we use the prefix fragment? And our flag which says, okay, did we use suffix fragment? Okay? And if we want to add another fragment, if we want to extend this fragment, we can just iterate through all of the cuts. So we can just iterate through all of the cuts. We can do this incrementally, so we can find whether this piece we are cutting, whether it's an infix or prefix or suffix piece, and then do the correct formula here. So we will not go into details about the recurrence, but we can see what is the time complexity of this solution. So in the state, we have to take the length and the number of cuts. So the number of cuts is k, the length is n. This only takes 1 bit each. And then we have to iterate through all of the lengths. So this solution is k times n squared. this is for the numbers from the task statement. This is too much, and actually we can do better here, because let's see at this optimal solution. So, what kind of infix fragments we would like to have? Of course, we would like to have the longest infix fragments here. So actually, if we have our starting sequence, we can calculate what are the lengths of the longest fragments. And actually, if we want to put some X fragments here, we approximately need to use twice as much cuts, because for each infix fragment we have to cut it from the left and from the right. Well, I say approximately because we have some additional cases here. So first of all, we have cases in which we have to take into account the prefix and suffix fragments, which are quite different. But also we have to take into account the cases in which we have some fragment which ends with the dynamic scene, and this fragment touches the end of the end or the front of our string. Then we also have to take extra care about these fragments. But actually, this can be done as making several cases in our code, in which we assume. So we can assume that we use the first fragment which touches the boundary of the string, and we use it like as the suffix. And then if we have several different cases, then for the prefix and the suffix, then with its left, we can just take as much longest strings as possible, and then it will give us either linear solution or n log n if we just do the sorting here. So that would be an n log n solution. So overall, this task is not very difficult, but you have to consider different cases, and it can be easy to miss one or two. Okay. So let's go back to the yesterday's tasks, and let's go with the task Godzilla. So in this task, we had a directed graph, and this graph represented a network, a cable network, in which the television signal is transmitted. So, possibly in each of these nodes we have some houses with the television sets, and we want to transmit the signal to all of these houses. And if we put some transmitter in the node, so let's say we put a transmitter here, it will transmit the signal to all of these nodes which are reachable from this node, but we have to take into account the direction of the edges. So actually, from this node, these are reachable. And we want to put signal in some of the starting nodes in order to have in such a way that the signal from these nodes will reach all of the nodes in the graph. And we want to put as little as these nodes as possible. So actually, in our graph, we can make the starting nodes these guys. So actually, these guys have no incoming edges into them. So we will have to put the signal here in order to them having signal. And actually, all of the nodes in the graph are reachable from them. But it's not the case that it's sufficient for us to put the signal into the nodes which have no edges coming to them, because let's say that we have this case. We have some node, we have some edges here. So actually, both of these nodes have an edge coming to them, but if we don't put any signal either in this guy or this guy, they will don't get any signal. So we have to select one of these guys. For instance, we can select this one in order to have the signal in every node of the graph. Well, and actually, if you solve some problems with the direct graphs, there's this notion of strongly connected component. So a strongly connected component is a part of a graph in which every node is reachable from every other node in this part. So for instance, this maybe let's take the red one. So for instance, this part is a strongly connected component, because from every node you can reach any other node in this component. So also this part is strongly connected, and actually, yeah, the rest of strongly connected components are just the simple vertices. So first of all, we can observe that if we have a strongly connected component, then it's necessary to put at most one, to select at most one node in this component. Because if we select one of nodes in the component, every other node can be reachable from this node. So it suffices to select at most one. Actually, it doesn't matter which one we select. Everyone will be good. But not in every strongly connected component, not in every component we have to select a node, because there are some components in which are reachable from other components. So actually, we do not have to select this guy because he is reachable from some other components. So, and using the same reasoning, we do not have to select any nodes in this component because they are reachable from other components. So the only components which we are concerned with are those components which have no incoming edges. So actually, in our picture, these four components are components with no incoming edges, and we have to select one node in every of such component. So in this graph, the minimal number of selected nodes is 4, and this is precisely the number of strongly connected components which have no incoming edges. So if we want to, so first of all, we can calculate the partition of the strongly connected components, and then we can compute the graph of these components. I mean, we can treat every component as one vertex, and we have this graph, and we can calculate how many edges are coming into every component. And this there are known algorithms for this, doing this, and the runtime is linear in the size of the graph. But our problem was a little bit hard, because okay, we have this network, and we have to provide select some nodes in order to transmit the signal into every node of the network. But there is this Godzilla from the title of the problem, and Godzilla comes and eats edges of the graph. So it will every day it will eat one edge of the graph. So after each day we will have to possibly we will lose some connectivity, and we will have to add some more nodes in order every node will have the secret. So for instance, let's assume that Godzilla comes and takes this one. He takes this edge. So then this will not be a strongly connected component anymore. So if we lose this edge, we will lose this component. And we will have to, so actually in this case we won't have to add another transmitter. We will have to just remove this selection, and we have to select this node. So actually the number of nodes we selected, it does not change, but we can have a bigger problem. So for instance, if so let's say that we remove, okay, so well, we can just remove this edge. So in this case we will once again lose the connection between those two nodes, and then we will have to add another select another node here. So our answer will increase. And we have some queries in which Godzilla eats subsequent edges, and after each query we have to answer what is the minimum number of nodes which has to be selected. So we can do, if we have S queries, we can do, so say we have S queries, we can just start all of them from the beginning. So we can just, for each query, we can just calculate the strongly connected components once again. And it's not easy to see if we can do better, because if we remove some edge, then probably a strongly connected component which contains this edge, we will split into some smaller components. And if this component is big and will split into several smaller ones, it's not easy to see whether we can do something much better than linear time. But we can do a trick here, because our solution don't have to be online. It means we do not have to answer, well, each query instantaneously. So we can like read all the queries first, and then answer the queries at the same time. So we can do a trick here, which is, let's reverse the time. So, because removing edges is somewhat difficult. So think about if this graph was undirected. So then removing edges was be like to some connected components will break apart. But actually, if we if we are adding edges, we are just merging connected components. And actually, we have good data structures to merge connected components in the undirected graph. Yes, it's just a fine tuning. So we can merge them fast, but it's not clear to see how to unmerge them. So actually, if we have the problem in which we have undirected graph, and we remove some edges, and we are asked whether some vertices are still connected or not, and our problem is not online, we can do the same trick. I mean, we can reverse the time, and we can first remove all the edges, and then we can add the edges from the last ones, and we can add the edges to the graph, not remove them. And for the undirected graph, we will just do the fine-tuning union, and that will give us a pretty quick solution. So let's try to do this here. So let's input all the queries. So let's input all the edges which were eaten, and let's remove all of them from the graph. And then we will add them from back to front, and this will give the answers to us, and then we will print these answers once again from front to back. So the question is how we update this graph when we just add some edge and not remove some edge. And this is not very easy, but at least we have some hope based on the undirected version. So the solution is as follows: we will maintain some partition of the graph. Each node will be in some subset of the graph. So actually, we will first of all, every time in our solution, we will be tracking which nodes are in the connected components which does not have edges which coming into them. So let's assume that we have m such. M is the graph. So let's say we have. I need some. Okay, let's see that we have some p initial components. So these are components in which we have to put some selected nodes. And we also have the rest of the graph. And from each of these components, we have some edge to the rest of the graph. And we have so in each component we also have some edges, but there are no edges between these components. And actually we also will maintain some partition of this graph. We will have sets B1, B2, up to BP. And if a node is in the sets BI, it means that this node can be reachable from the initial structure connected component AI. So if vertex B is in BI, it means that it's in BI if the other way around. If this vertex is in BI, then V is reachable from AI. Well, a vertex in the graph can be reachable from different components, but we will store only one number. So if V is, let's say, reachable from the first and from the second, it can be in B1 or B2. It does not matter to us. We only have to know at least one component which this vertex is reachable from. And of course, vertex V has to be reachable from some of these components, because we assume that we have the, that like this picture is correct. Yes. So every node is reachable from at least one of these components. Okay. So now we want to add an edge to the graph, and we will have different possibilities here. So, okay, so let's say that we want to add an edge from V to U, and let's consider different cases. So the first case, it will be quite easy. So what if the vertex U belongs to some of the sets B? So again, we can consider different cases here. So for instance, we can have an edge from some component A to some other component B. So let's say we can have an edge from the vertex in A2 to some vertex in B. So what does it change? Like, does it change anything? It does not, because still, like this component, this edge is like the forward edge in the strongly connected components. So it will not merge any of the. It will not change these guys. Yes, this component will not get reachable from any other part of the graph. And also this node here, it belonged to BP, so we said that it was reachable from AP, but it's still reachable from AP. So we do not have to change anything from this node. So for this kind of node, we do nothing. Okay, so this was the one example of this edge, but also we can have an edge which is in one BP component, or which comes from some other BP component to some, for instance, from B2 to BP, and then again this edge doesn't do anything, because still these nodes were reachable from A's, and they're still reachable. So for each of these nodes we just do nothing. Okay, so let's consider the case if we have a node, if we have an edge which ends in some of these components. So actually here we will have some work to do, because we can merge two components here. So every time we add some edge, our answer will be either the same or it will decrease, because some of these starting components can get reachable from the others. So if we have an edge from A1 to A2, then every vertex in A2 will be reachable from A1. So we don't need this guy to be selected. So we can just like merge these things together. But also we have to consider cases when this edge comes from different part of the graph. So actually let's do the general case here. Okay. Okay, so let's say that we have an edge which points to this component, and we have some vertex D here. And let's see what are the options for the vertex V. So let's say the vertex V is connected is in some bj. Well, okay. Let's first of all let's consider the case it's in B. It will be an easy case. Okay, so this guy is here. Okay. So this edge comes from BI to AI. So actually we know that vertex B is reachable from this component. Yes, because this is the definition of the vertex to be in BI. This vertex is BI, so we know that there is some path from AI to this vertex, and then we add an edge from this vertex back to this component. So actually that means that this vertex is becomes in the component AI. So we can change this vertex. So we can move this vertex to AI. And this operation can make that some other vertices will also have to move to AI. Because let's say that we have an edge here from W to V. So if W is also in B2, then we know that there is a path from A2 to B2. So there is a path from A2 to W, and we have another path here. So actually, we want to move the vertex W also to AI. So what we will do, we will start from vertex V, and we will traverse this graph in the backwards. So we will traverse the transposition of this graph. And every time during this traversal, every time we see a vertex which belongs to BI, we move this vertex to AI. But during this traversal, again, either vertex V or any other vertex, we can see the situation that this vertex belongs to AJ or BJ, where J is not equal to I. So what happens there then? So that means yeah. So for instance, we have this thing here when we got from A1 to A2. So that means that the strongly connected component AI is reachable from strongly connected component AJ. So the thing we will do, we can put all of these vertices into BJ, because these vertices are starting to be reachable from AJ. So we can, so actually we can put the whole component here, because well, these guys are strongly connected. So we can do, if we find this vertex, we can say that Bj is equal to Bj plus Aj plus A. I don't get it. Okay. Oh yeah. So to Bj we will add Ai and Bi. Okay, because that means that these guys are reachable from the strongly connected component AJ. So all of the nodes which are reachable for AJ are, well, some of it's called, but they can be in BJ. So we are just adding these two guys to BJ. And that's it. So that's all of the cases. And after considering this, we will have a correct draft. And one thing to consider here: what is the time complexity of this solution? So for every edge here, we did some search through the graph, and let's see how long does it take to do all these searches. So actually, when we are searching the edge, so then this edge, the vertices, the ends of this edge are in different sets. So first of all, we have like use because if they're in the same set, we don't have to change anything. And afterwards, if we go through this edge, either we move the vertex to the node AI, so either both of the edges, both of the ends will end up in the same set, or we merge some components, and again both of the ends of this edge will end up in the same set. So after we do some traversal, the ends of this edge will end up in the same set. So we won't be doing any word traversal with this edge. So actually we will go through every edge at most once. So that will mean that this solution has the time complexity of almost linear, but we also have to make this union here. But again, we can use the find a union technique, and if we code it correctly, then it will give us almost linear solution. Yeah, up to the iterative logarithm is smaller than 5 in our practical approaches. So this will give us almost understanding. Okay, so that is good enough.
Tomasz, I didn't understand the complexity analysis. Why do you
Okay, so if I go through the edge, then both ends of the edge are in different sets.
You only traverse an edge and what's it? They are the same sets.
Yeah, because okay. So if the edge is in the same, if it's in the same set, so that means that we we don't have to go through all of these edges, because all of the if they are in the same set, so all of the edges are like in the same class. So if the edge is in the set AI, so every node in AI is reachable from each another.
So then you have like 3 nodes. You have this one, and then you have a set it's the same as this one, but then this one is different. How do you reach this one?
Okay, so maybe let's. Do you want to make an?
No, there's 3 nodes. Like the first is from BJ.
Okay, the first one's from J.
The second from BI, and the third from BI. And you have like BJ to BI and BI to BI.
BJ to BI.
Yeah, BI to BI. And now you're at the third node. How do you eventually reach BJ?
But the thing is, why do you need to reach? So what is the edge you are adding? So what is the edge VU?
BI, the last one, to AI, to some AI.
Okay. So this one is to some AI, yes? Okay. Okay, you're right. Okay, so it was not. Yeah, Yeah, but in this case, all of these nodes will end up in AI.
Yes.
So after, if the nodes end up in AI, then we will not traverse them anymore.
In the algorithm, how do you check? How do you put them in AI?
Okay, so if they, so these are in BI, and if I find the node from BI to AI, I just mark them that these nodes are in AI.
So you won't have a problem with BJ afterwards.
No. Okay, maybe we'll take this one to offline. So after the thing will. So actually, I think we have to be more precise in seeing what is the time complexity. Yeah, but the thing is, if doing correctly, this will get us the correct complexity. Okay, but we still have some more problems to say about, so let's leave it as now. Okay, so maybe from the yesterday's contest, we will talk about the museum problem. Okay, so in this problem we have a museum, and in the museum we have some guards, and the guards are watching over some jewelry. So we have guards, and we also have some jewelry. And we want to, the hero of the story wants to rob the museum. And he wants to take as much of the jewelry as possible. So each jewel has some value in it. So let's say this jewel has 5, this jewel is worth 4. And we have some guards, and these guards are seeing the jewels only in the certain angle of view. And each guard has the same angle of view. Guards have different positions, but they always look at the same direction, and they always look at the same angle. And so we don't want to steal, well, the hero don't want to steal the jewels that are watched by the guards, so it's pretty safe for him to steal this one, but it's not safe for him to steal those ones. But he wants to bribe some of the guards that they will be not watching during the stealing. So each guy has also the price of bribing. So for instance, we can bribe this guard for 7, and this guard from paying 1. So the question is, what is the maximal profit we can get after bribing some guard? So in this case, it's not optimal to bribe this guard, because after bribing him, paying 7, our hero will gain at most 3 in the stolen jewelry. So this will not give him any profit. So he won't bribe this guard. But bribing this guard, as it makes profit, because he will pay 1 for bribe, and he will get 4 in jewelry. He won't take. Well, actually, bribing this guard is also not sufficient to take this jewelry, because this is also seen by this guard. Yeah, this guard has the big field of view. So actually, bribing this one is not sufficient. So the optimal solution is to write this one and get these those. So we have 5 plus 4 minus 1 from bracket. And this is the optimal outcome. Okay, so what to do about this task? So first of all, it looks like a geometrical task, but in fact it isn't. Let's simplify it a bit, that we get rid of all the geometry. So in the task, the field of each, the angle of each guard was given by 2 numbers. So if we put a triangle here, these 2 edges will have length of h and w respectively. So first of all, we can transform all of the coordinates here in order these angles will have 90 degrees. So we can just multiply all of the x coordinates by h, and we can multiply all of the y coordinates by w. So we can just make it xi multiply by yh, yes, and yi multiply by w for every guard and for every jewelry, and that will change our picture in the sense that all of these angles will be 90 degrees. So all of the fields of vision will change to something like that. And also we will retain this thing that all of the jewels that were seen by the guard in this setting will also be seen by this guard in this setting. And moreover, we can rotate this by 45 degrees. And again, rotating by 45 degrees is also an easy operation on the integers. We can, like, for one of the coordinates, we will take the sum of the coordinates, and for our coordinate we will take the difference of them. Maybe with other example signs, but the thing is that we can do all of these operations using integers. Okay, so what we have here? So first, thanks to that, we changed our problem into something like that. Okay, let's move it by 45 plus 90. So let's move it by 135. So in this case, every guard will be seeing the 1/4 of the plane. This part of the plane which is above him and right to him. And we have several of these guards. Okay. And also we have guards, and also we have some jewelers. Okay. And we will do. We will use the sweeping technique here. So we will sweep our plane with the line. Let's say that our line will be vertical. So we will be sweeping from left to right, and every time we want on this line, we'll have some data structures which will contain all the necessary information we need from the left side in order to construct the first of all, to say what is the optimal solution for the things which are only on the left side, and also all the necessary information which will allow us to add some new things from the right side during the movement of the sweeping line. So we will have some data structure here, and this data structure will be a range tree in which we will have some values. So the thing is, what is the important information about the left side, which has to be in this data structure, which would still need to the right side. Okay, so we have some jewels on the left side, and these jewels are only affected by the guards which on the left side. So as long as we take into account these jewels, whether they are taken or not, these jewels will not affect the right part. But also on the left part we have some guards, and these guards can affect the left part. Because for instance, this guard is, if he's not bribed, then he sees all of these jewels here. But we do not need to know precisely which guards are bribed or not, because if we bribe this one, so he will be seeing all of the jewels which are above this line. Yes? He will see all of things above this line. So actually, for the guards which are above him, so for all of these guards, it does not matter if they are bribed or not. If this guard is not bribed, then it does not matter whether these guys are bribed or not. So actually, we will be interested in knowing which is the lowest guard which is not bribed. So we can be interested, okay, so we can say this guard is the lowest one which is not bribed. So this line we will divide the jewels which are seen by some of the guards from the left part, and the rest of the jewels are not seen by the guards from the left part, because we assume that all of these guards are bribed. So in the data structure, we will have the optimal result from the left part, the optimal, like bribing the guards and attacking jewelry, for every this line. So assuming that the lowest not bribed guard is on this level, what is the optimal solution from the left part? And all of these numbers we will be storing in this data structure. How many are these values? I mean, we have to consider each line for each guard. So if we have n guards, then we will have at most n values on this line. Okay, so we know what the data structure is. Now we have to update. So we will be moving these data structures, and we will be we'll be stopping in some events, and we will have two kinds of events here. The first event is our sweeping line stops at some jewel, and the second event is our sweeping line will stop in some guard. So for the first case, so let's say that our sweeping line moved and is stopped in some jewel. So we would like to. So we either take this jewel or not. The thing is, the decision whether we can take it or not only depends on the guards which are on the left side, and if the lowest not bribed guard is above this jewel, then we can take it, and otherwise we cannot. So actually, for all of the lines which are above this this dual, we can add the value of this dual to the optimal solution for all of these lines. And for all of the lines which are below this this dual, all of these lines means that there is some not bright guard which sees this dual. So for all of the states, we cannot take this this dual. So we only update these states which are above the dual. Okay, so this was the dual, and now we have the second type of event when our smoothing line encounters a guard. So we have several cases here. So yeah. So let's consider all the lines which are above this guard. So all of these lines means that the guards which are not, the lowest guard which is not bright is on the line. So if this guard is below the line, we have to bribe them. We have to bribe this guard. So for all of these states, we have to subtract the cost of bribing this guard. Similarly, for all of the lines which are below, that means that some guard is there is some not bright guard which is below this one, and all of the jewelry which sees this guard are also seen by this lower guard. So for all of these lower states, we do not have to do anything. And there's one last state. It's the state of this line. So the state for this particular guard. So what can we do? So what can we do here? So this line will say, okay, this is the lowest guard which is not bright. So okay, we do not have to bribe this guard. But let's take a look. What is the optimal solution for this guy? So actually, all of these things will be seen by this guy, and this is the lowest guard which is bright. So all of these guards here on the left part, which are below this guard, which must be bright. So we cannot use these states. We can only use these states. So which are seeing that the lowest guard not bright on the left part is higher than this guard, and all of these states are equally okay for us. So we can just, in calculating the profit for this guard, we can just take the maximum of profits of all of these the lines which are above this line. So we're just taking the maximum from the tree. Okay. So we stopped on every guard and on every jewel. Let's say that we have the sum of the guards in the jewel is equal to n. So we have to perform some n steps, and during each steps we update the data structure. During the update, we either update some, we add some value to the range in this data structure, or we take maximum in some of the range. So this is like this can be done using the range tree, and every operation will have the logarithmic time. So then the overall solution for this task is n log n. And this preprocessing can be done like in linear time. So this is the fine complex. Okay, so I think that would be it for the yesterday's tasks. I also would like to give some hint to the task from the first day, because I said that the task postman can use some dynamic programming, and we have we see some dynamic programming on the trees, which requires us to make an n-square solution, and we use the same ideas for the postman. So, but I will only give you a hint, not the whole solution. So in this task, we have a tree, we have a rooted tree. And we have two postmen. And they have to start from the root, and they have to visit all of the nodes. And each node must be visited by at least one of them, but they do not. And they want to finish to visit the last node as soon as possible. So for instance, one guy can go like this in the tree. So that will take him like the time 1, 2, 3, and 4, and the other guy can visit the rest of the tree. But perhaps this guy can go back here and go here, and this guy only. Oh yeah. So this guy can go here, and this guy can only visit these nodes and can end here. So these are different possibilities here. And n was at most, let's say, 3,000. So we are going here for n-squared solution. So actually, we can start with the easier version of this problem, in this version, every postman has to go back to the post office. So we are interested in what is the minimal time for both the postmen to visit all of the nodes and go back to the post office. And then the idea for the dynamic programming is as this. So we can have some subtree. And let's say that this subtree will be visited by both of the postmen. And let's calculate what is the minimal time of visiting. So it depends on, well, if we only calculate the minimal time, then perhaps some of the postmen will take the different amount of time than the second one. So let's say that first postman take T1 and the second postman take T2. So if we only calculate the maximum time, so maximum of these two numbers, and then these postmen can go, so they're going into the tree and then out of the tree and possibly visiting some more trees. So we will be needing this information. What is the time in which the first postman go out of this tree, and what is the time the second postman go out? So actually the minimum will be too less information for us. But we can do as follows. We can just make we can fix the amount of time which is used by the first postman. So let's say that the first postman can use this time on the tree, and he can visit any nodes he would like using this time. And we can ask, what is the minimal time for the second postman to use in order to visit all of the vertices in this subtree? So what is the minimal time of the second one, assuming that the first one has time t1? Actually, so if we compute this, that will give us all the information we care. Because if we have the bigger tree, and the first postman has some time in this tree, T1. So then we can ask, okay, so in which subtrees the first postman can go, and in each subtree how much time we will give this postman to have. And then for each subtree we can calculate what is the minimal time for the second postman to visit the remaining nodes. And then it will give us the time T2 for the whole tree. And the interesting part is here that what is like the maximum time for the first postman to visit all of the nodes in the subtree. If the subtree has, let's say, S nodes, then the maximum amount of time to visit all of these nodes is like to go and traverse all of them is 2s. So this time is proportional to the size of the tree. Actually, if we can say if this postman has to go out of the tree, then every edge which is visited by this postman has to be visited twice. So actually, we know that this time is even, so we can divide it by 2. So we can like make it even like this. So for every tree, the first postman will get from 0 to s time. So for every tree, we will have this dynamic programming, which will say, okay, we are in the vertex and we are given some time for the first guy, and what is the minimal time for the second guy to visit this tree. So this is the idea. Well, the tricky part is how do we merge these subtrees, because here we have also different possibilities, because if the first guy goes to the first tree, he will be using this edge. But if he will say, okay, we will not putting this guy in the first tree, then the second guy will have to visit all of these nodes in this tree. But then this edge will not be used by the first guy. So we have some cases here. But overall, this can be done in using this technique we seen in one of the lectures, and this can be done in n² time. So this is the slightly easier version, in which every guard has to go back to the post office. We can, in our version, the guards can finish sooner. So as long as the last letter was delivered, they can just take their time. So the idea is the same, but we have slightly more cases. We have to consider also in this DP whether the first guard goes up of the tree, or not the guard, but the postman. Whether the postman goes up of the tree, or whether the postman finishes his journey in some nodes of the tree. So we will have like the flag for the first postman. Well, it will be 0 or 1. Whether he has to go up, or whether he can finish in this tree. And also for the second one, we also have this. So that will get a little bit tricky in doing all these cases correctly, but the general idea is the same. Okay, so the task pizzerias from the first day, it also uses similar techniques, but then we have to think a little bit what is the thing here, which we are considering in the dynamic program. But also it can be done this way. Okay, so it's 11:30, so I think we will finish it for today. There's some one thing I would like to say. I didn't have time to talk much about the strategy from the team competition, and I think it's also very important not only to be able to solve the problems, but to have like the good strategy for this kind of competition. Because well, you have you also need to, like, first of all, know your team, and secondly, you have to, like, cooperate in the team in order to use all of the resources you have. And usually you don't have much resources. For instance, you have only one computer, so you have to, like, use it wisely. But I saw that in the previous years of the school, you have the videos on the internet from the lecturers, and I saw that in some of videos the lecturers are talking about the strategy. And I think I don't have, like, much to say apart from the things that they were saying. So I just encourage you to take a look at this video and just also, like, get some information about what the strategy, from the strategical point of view, what can you use during this competition. Okay, so about the competition, today will be an individual one, and this will be the last one. So we will not have the possibility to talk about the problems for this competition. Perhaps I will put some hints for the problems in the mailing list. Okay, so this was the last lecture, and I would like to take this opportunity to thank all of you for all the all the work you take in order to prepare for the competition. I saw that you work hard on the problems during the competitions, but also during the night. So it was really it's really good to see the people that are motivating to do practice. So it's also good for me to see you performing well, because it gives me motivation, like to try even better for this teaching stuff. And I also like to thank you for all of the kind words because I have the possibility of talking to some of them during the lunches and the suppers, and that was really nice. So thank you for your warm welcoming, and good luck on your competitions.